All right, so next we have circular motion. That means we talked about in previous chapters, mainly in chapter 3, when we talked about circular motion, that object, when it undergoes a circular motion, we would say that, okay, so that's due to the fact that there's a radial or centripetal acceleration, and that centripetal acceleration was equals speed squared divided by the radius of that circle. And this acceleration was responsible for changing the direction of the object. Well, now that we learn about Newtonian dynamics, we know that there is no acceleration without a force. The reason there's acceleration is because there's a force acting on the object. So if there's a centripetal acceleration, which is pointing toward the center, it means there's some kind of force pointing toward the center, which gives us that, centripetal acceleration. And that's what we have. So net force equals mass times acceleration. If that acceleration happened to be the one that changes direction rather than speed, then we can say that's a centripetal acceleration. And that acceleration, since it equals speed squared divided by radius, then the net force that gives you the circular motion is equals to mass times speed squared divided by radius. And then we can say this is then the net centripetal force that gives you this. So mv squared divided by r. This is the magnitude of the centripetal force, or the net centripetal force. Direction is simple because it's always toward the center. That means that force, or the net force, always acting toward the center. And this is not some kind of new type of force. Any force can be a centripetal force. A normal force, friction, tension, push, pull, all of those type of forces can technically be a centripetal force. Okay. All right, so the centripetal force, again, causes a change in the direction of the velocity vector. All right, so then think like this. Right now you have an object that is connected by a rope, goes around with respect to the center. And the rope, well, the rope gives you, tension force, right? That means the tension here is a centripetal force acting toward the center. Then you can say that, okay, so the tension equals to mv squared divided by r. And if the only force toward the center is this tension, then tension is the centripetal force. One thing we also have is this: at any instant, the object is moving perpendicular to that force. That means the velocity, remember, is tangential velocity, right? Tangent to that trajectory. So for example, this here, right here, that instant, right, it's moving with this velocity. And if you cut the cord, right, then it actually will continue moving with that velocity that it had at that instant. So that means if it's here, you cut it, then it's going to just continue moving like that. That means at any instant, it moves whatever velocity vector it had, at that trajectory, during that trajectory. Generally, what we can do here is this. You can have two types of circular motion. One is a vertical circular motion, which you see in the picture. That means you have an object that goes around like this in a vertical circular motion. So this is vertical. Or it can have a horizontal circular motion. Horizontal, which is, here's the object and kind of goes like this, along the horizontal plane, like that. Kind of goes around like that. Again, with respect to some center point. So you're gonna have to see that we will have some examples for both, horizontal and vertical, and we will see, let's say, what type of forces generally acting on the object during those, vertical or the centripetal, vertical or horizontal circular motions. Because, for example, gravity is completely neglected for the horizontal circular motion, because gravity always acting down at any instant of time, and it's never a centripetal force because it's not pointing toward the center. But for example, in the vertical, so the gravity here acting down, not a centripetal, but here gravity acting toward the center. Here gravity acting, down, so not toward the center, but here it's not acting toward the center, but it's on the radial line, which makes it a centripetal force, or the part of a centripetal force, when we see that type of problems. All right, so let's look at then an examples. So we have a 0.2 kilogram stone is whirled in a horizontal circle, horizontal circle, right, at the end of a 0.8 meter long string. The string makes an angle of 20 degrees with the horizontal. Determine the speed of the stone. All right, so here's the picture of that, so you guys can see sort of like what's going on. So the angle theta, right, you can see that for the, let me see, the 20 degree with respect to horizontal. So that's the angle theta that we're given. Okay. Sometimes the theta can be given like in terms of that. So you have to be careful. Okay. All right. So for this particular, let's say example, you can say that we are given, the mass, which is 0.2 kilograms. We're given then the theta, which is here 20 degree, with respect to horizontal. And also we're given the radius. The length of the string is basic, no, sorry, that's actually not the radius. So we're giving the length of the string, okay, length of the string, and radius in this case, basically kind of like equivalent to this, distance x, right, that it has, let's say with respect to that central, vertical line, okay. And, in this particular example, you can see that we can technically calculate that, right? Because if this is L, right, because this is also L, and that's the theta, then, uh, you can use that to pretty much find, whatever that X is in terms of using that, which in this case basically becomes, let's say the adjacent side for that angle, right? So then it can be said R, which is same as X, equals L cosine of theta. So, in a way, we are given L, which is 0.8 meters, and we're given theta, and you can see, right, we should be able to calculate then R, which is the radius. And we are trying to find that. We are trying to find the speed. Okay, so what is the speed? Okay. Now, the way we will approach this problem in previous examples, right, that we did, any type of circular motion, we saw that, all right, so there's an equation where acceleration equals speed squared divided by r, okay? Or there was an equation where speed equals to 2 pi r, which is the circumference or distance, right, divided by the period, okay? Now, we don't have anything about period in this example, so in a way we can rule out this type of, way of calculating the speed. But this one actually, reasonable. That's what actually, we should be able to use that. That means we need to find acceleration first, and we are given radius, right, or way to find that, and we can solve for the speed. So that means I need to use the Newtonian dynamics to solve for the acceleration. And then from that, I can get basically the speed. So let's see what we do. So I'm gonna, you can see, right, I'm gonna then make a, a free body diagram where my free body diagram basically goes like this. All right, so object is the, a stone, right? So I take this up to be positive y, toward the center, my positive x. And then you can see the forces acting on the stone is the gravity, mg, and then the tension here, okay? So then I make a table. So I have tension, and then I have the, weight. F of g or W is the same for weight. And here's net force. Okay. Now, the tension in this case becomes a two-dimensional force. So you can see, right, you can technically then take the tension and break it down into two components, right? Here's a component, this is Tx, and then here's a vertical component, and this is Ty, right? So those two components can be written here, which is as T cosine theta and T sine of theta, because if I'm taking to the left as positive, tension is basically in the first quadrant. Weight, another case, is a negative y direction. All right, so it's a horizontal. So this guy gonna go around horizontal direct, circle. So there's no vertical acceleration, but there's a mass times centripetal acceleration in the x direction. So mv squared divided by r. Then what I get here, two equations from here, which is T cosine theta equals mv squared divided by r, right? And then equation 2, T sine of theta, technically minus mg, so equals to, mg. And that's what I get from here. All right, so then from here you can see that I can take this equation 1 and 2 and use them to find, let's say, because what I have, think like this, what I have here is this, right? So T cosine theta equals mass times centripetal acceleration. So then technically I can use this to solve for acceleration and then plug it into this equation. Or I can just directly say this is, mass times speed square divided by r, right? And then just use this to directly calculate that. Now let's see how we can do that. Okay, I'm going to take equation 1 and equation 2, and I'm going to, divide them. I'm going to divide equation 1 by equation 2. That means left side divided and the right side divided. So if I look at the left side, then I have t cosine theta over, t sine theta. I cancel the t because I don't need to know anything about the tension. And whatever I get here is this. Cosine theta over the sine theta, which is basically a cotangent theta, right? On the right side, I have then mass mv squared over r divided by mg. Mass can cancel out. And what I get here is v squared over rg. Okay, that means cotangent theta equals v squared over rg. And I can rearrange and say, okay, then v squared is equals to rg times cotangent theta. And then from this, where we realize that r equals L cosine theta, then I can say then v squared equals to L cosine theta times g, then times cotangent of theta. And then since v is squared, I take the square root of both sides. Okay, and I just calculate that. So v is equals to square root of 0.8 meters times cosine of 20 times 9.8 times cotangent of 20. And then solve for v, which will be then 4.5 meters per second. There you go. That's the answer for this problem. And you could see, right? So we get equation 1 and 2, and then we divide equation 1 by equation 2. That means you can divide, you can multiply, you can subtract, you can add them equations together, right? Once you get your equations, the easiest way to eliminate unknown is basically do one of those functions. All right, so here's another example. 0.8 kilogram airplane pilot pulls out of a dive by following at constant speed of 180 kilometers per hour the arc of a circle whose radius is 300 meters. Okay. At the bottom of the circle, what are the direction and magnitude of this acceleration? And what is the net force acting on him at the bottom of the circle? And what is the force exerted on the pilot by the airplane seat? All right, so let's see what we have. So generally, in terms of, let's say this type of problem, right? So you can see that we are talking about, like, let's say the bottom part of the, circular motion. So in a way, something like this. So this, and then here's the pilot undergoing this type of, circular motion, where this is basic. This is, let's say, the radius r with respect to some center. All right, so think like this. Now we're talking about pilot that's sitting on his seat, right? And what I have here is this as being the center. So two forces that are acting on him are the normal force and gravitational force. Okay, normal force, gravitational force. Now, one thing we know is this: even though speed is constant, the pilot is undergoing sort of like a vertical circular motion. That means there has to be a net force in that direction to give us centripetal acceleration, right? So that has to be net centripetal force in that direction, right? Which means normal force has to be greater than weight. That has to be sort of like, let's say, given to us. Okay. So then what we do here is let's say we understand that those are the forces acting on it at the bottom, and part A is asking let's say if I write down what's given to me. So I'm given the mass 80 kilograms, I'm given the radius 300 meters, and I'm given the speed. Let me put it in terms of 180 kilometers per hour. Okay. So what we need to find first, let's say, is the acceleration. Okay. All right, so acceleration is the easy part because I know that acceleration is speed squared over r, since it's a centripetal acceleration. And I'm already given speed. 180 kilometer per hour, and I have the radius, which is 300 meters. I can just take this ratio, square that, and find it. The only thing is the kilometer per hour is not the units that we want, so we have to change that. So we need to find this in terms of basically, meters per second. So 180 kilometer per hour, where 1,000 meters is other way around, where 1 kilometer is 1,000 meters. So then we can cancel kilometers like this. And then 1 hour here we have 3,600 seconds. And this whole thing squared divided by 300 meters. Then we get centripetal acceleration as 8.33 meters per second square. And the direction has to be, remember, toward the center. So in a J-head direction, let's say in this case. Just put it like that. All right, so then part B, it says, what is the net force acting on him at the bottom of the circle? Well, one thing we know about the net force in the centripetal direction, or for the centripetal net force, is equals to mass times centripetal acceleration. Well, we have the mass, 80 kilograms, and then we have the acceleration now, 8.33 meter per second square. Then I can calculate this to be 667 newtons, again in a J-head direction. As I said, right, there has to be net centripetal force in that direction. Part C says, what is the force exerted on the pilot by the airplane seat? Now, what I have here is that I have a net centripetal force, 667, but net centripetal force is due to the two radial forces acting on the pilot, which is the normal force, I can just put it like that. So normal force up and weight down. And this is equals to 667 newtons because this is my net force, which means that normal force is equals to 667 newtons plus the weight, which is basically nothing but mg, right? Which is, 80 times 9.8. I plug in everything together and I get 1.45 kilonewtons. Again, it's in the J-head direction because normal force acting upward. That's why, like, normal force is 1.45, gravity is acting down, so then net result is basically their difference, pretty much. So that's what we get from this type of problem. Here's another one. A small object of mass m1 moves in a circular path of radius r on a frictionless horizontal tabletop. It is attached to a string that passes through a small frictionless hole in the center of the table. A second object with a mass of m2 is attached to the other end of the string. Derive an expression of r, which is a radius in terms of m1, m2, and the time period t for one revolution. All right, so let's see, that means, it's asking for the expression. That means there, it has to be some kind of like formula in terms of making sure that there's m1, m2, and the period included in the equation. All right, so we can see that what we're given is basically an object that goes around a horizontal, circle, right, on a table. And there's an m2 over there where the mass 2 is basically acting as a central force. That means we can say that the tension here acting on m1 is the same tension acting on m2, which is equal to its weight because m2 is just hanging there. Okay, that means we can kind of look at it in terms of that. So breaking into two parts. First, look at the m2, and if I'm looking at m2, I can see that there's weight 2, which is m2g, and there's a tension acting on mass m2, but it is in equilibrium. So m2g minus t equals 0. So m2g is equal to the tension. That means tension equals to the weight of the hanging object. For the system 1, which is m1, so it's kind of like, here's the string, right? So it is on the horizontal table. So there's a normal force. There's a, tension force. And this is the m1g, which is the gravity. Okay, so again, taking this to be x, this to be y, right? So I can see that, let's say if I do the table, here's the tension, here's normal force, here's weight for one. Generally, when at least three forces, I try to put the table here like that. So plus T, 0, 0, and 0 minus mg. This is 0, and this one is mv squared over r, which is for the net force. That means only the tension gives you the, centripetal acceleration. All right, so that means what we can do here is this. This was one equation, right, where T was equals to m2g, we get from the system one. From system two, we get equation two, where then T is equal to then m1 v squared over r. You can do it like this. And then equation three, which was n minus m1g equals 0. Okay, so we have those three equations. Well, remember, one of the things we have, I probably should do this. Tension force, I should just write it as f of t, because period t and tension t, both of them are t, is like confusing which one is what. So let me put this as f of t. The tension force is basically f of t, and then capital T then going to represent the period t. Okay, let's modify all of them. All right, so I think we're done. There you go. So because I don't need to have an equation in terms of, this t, all right? So for example, then I can see that f of t equals m2g, f of t equals also equals m1 v squared over r. So I can combine them. m2g is equals to then m1 v squared over r, right? They are equivalent to one another. But see, my expression for r, which I have in this equation, right? So you can see I need m1, m2, and the period. Well, I have m1, m2. Well, g is a constant, so I don't have to worry about that. But then I have a speed square. But remember that equation, right? Speed is equals to 2 pi r divided by the period. Then I can use this equation to replace speed in like, in this m2g is equals to m1, then times 2 pi r over the period square divided by r, which then gives me m1 4 pi square r square over r, which going to cancel the r at the bottom. That means my equation then will be m2g equals m1 4 pi square times r. And sorry, there's also t square over there. Then divide by t square, which is the period. Then from here, all I have to do is just rearrange and solve for r. That means move it here. Say r is equals to, then move t squared to the other side, becomes t squared times m2g divided by m1 4 pi square. Oh, I don't know why. Sorry, I don't know why I did that. That's there you go. That's my expression. Okay. Again, starting from here, where I have combined equation 1 and 2 together, because m2g is same as tension and m1 v2 squared is same as tension, and then replacing speed with the circumference over the period, right? Distance over time. And then from that, just rearranging and solving for r. All right, here's one more example. So there are a bunch of examples so you guys can see different scenarios and things like that. So you're swinging your younger sister in a circle of radius 0.75 meters. If her mass is 25 kilogram and you arrange it so she makes one revolution every 1.5 seconds, what are the magnitude and direction of the force that must be exerted by you on her? Model her as a point particle. And what are the magnitude and direction of the force she exerts on you? All right. So we assume that when you are, swinging your sister, you basically, let's say this is the sister, right? Swinging with some kind of, force like this. Okay, not necessarily like horizontal, right? That's going to be a little bit too intense, but sort of like at an angle like that. And then she will be kind of going around in a horizontal circle like that. Right? That means again, this being her, so some kind of force like this. Which makes the force here, let me do it like this, right? Which makes this force, if I put it at the center like this, you know, with some angle theta like that. All right. All right, so let's see. There's also another force acting on her always, which is the weight. So technically we have two forces, applied force and then the weight. Okay. And since applied force, if you see that in this example, right, has a component toward the center, right? If I break it down, there's a component toward the center, then I can say, all right, so then here's my table. These are my forces in X direction, Y direction. So I have F of A. Okay. All right, so here's F of A, and here's the weight, and the net force here is basically F of A has two components, and since the theta is given with respect to vertical axis, so the X component is actually F of A sine of theta, Y component F of A cosine of theta. First quadrant, positive, positive. Weight straight down, so minus mg. In the X direction, there's acceleration. In the Y direction, there is not. So we can say mv squared divided by r. That's for the, you know, X direction, you know, mass times acceleration, but it's a centripetal acceleration, right? Because, you know, there's a centripetal acceleration toward the center. All right, so we take that and then we set up our equations, set up our two equations. So equation one will be Fa sine of theta equals mv squared over r. And equation two will be Fa cosine theta equals, and basically mg, right? Because Fa cosine theta minus mg equals 0. That means they equal to one another. All right, so one thing we want to do here is to find the force. So for example, I need to solve for the, let's say, F of A. But I don't have, several things. See, we're given the radius, we're given the mass, and we're given the period. All right. But one thing we're not given is, for example, in this equation, like if I'm using that equation to solve, or this equation, if I'm solving for, remember, our goal here is to find F of A. But in all those equations, I have at least two unknowns, which means I don't have F of A and I don't have theta, right? That means I need to first find theta so then I can solve for F of A before I can do anything. So that means what we do here is we go back to equation 1 and 2 and try to solve for theta first. So, but in any case, so we have two equations, two unknowns, so we can work around that. I divide equation 1 by equation 2. You can see, right, F of A cancels out. It's okay for now because, I don't need to know what F of A is, for example, to solve for theta. Left side, sine of theta over cosine theta becomes tangent of theta. Right side, masses cancel out, and I have V squared over RG. So that's basically what I end up with if I do the equation 1 divided by equation 2. Now, I don't have V directly, but I have this. V is equals to 2 pi r over period, which means I can solve for that. I can solve for the, for this, or I can just say tangent of theta equals 2 pi r over the period square divided by rg, which will then end up giving me this. 2 pi r, 2 pi r over period square gives me then 4 pi r square, and then this divided by period square rg, where I can cancel the, one of r's. And then solve for theta, which will be inverse tangent of 4 pi r divided by t squared times g. And this I can do because I have r and t squared, right? I mean, period. 4 pi and g are nothing but constants. Plug in, 0.75 for r and plug in 1.5 for period t, right? Then we can just, use all of this to get 53.3 degrees. Okay. That means, plugging in those values, we can get that. Now that I have theta, I can come back and solve for the f. So for example, I can say f of a is equals to mg over cosine of theta, right? Using equation 2. And that's easy because I have 25 kilogram times 9.8 divided by cosine of 53.3 degrees. Now I can do that and solve as 410 newtons. There you go. Now that's the value of the applied force acting. Okay. Now the question is that what are the magnitude and direction of the force she exerts on you? Well, this is the direction, this is the magnitude of the force and direction obviously toward the center, right? So toward me. But let's say then the sister acting on me is action reaction pair. That means it's exactly the same magnitude, but the opposite direction. All right. The next couple of examples are going to involve circular motion, object going around the circle, but this is basically a car going around the circle. And one of the things we can do here is we need to understand that, for example, when a car, look at it. So we are looking at the car from above. So if you're looking at the car from above, what makes the car to be able to successfully, let's say negotiate the curve, right, is actually a static friction. So force that, works as a centripetal force and allows the car to turn is actually static friction between the tire and concrete. Now, there are two types of problems we can encounter, for this type of highway, curve. When the car is basically making a turn, you can look at what we call a flat, let's say flat road, which is also known as an unbanked road. So you can see right here, unbanked road. So flat or unbanked are the same. Or banked road. Banked road is basically not flat. That means the road is a little bit at an angle. Okay. In any case, the centripetal force basically acting on, unbanked road, that means when the car is on a flat surface, is friction. So here's an example. You can see, right, if the frictional force is insufficient, then the car will tend to move more nearly in a straight line, as the skid marks will show. That means, for example, if the car is here, for example, right? So it is moving, so the friction force is toward the center. Now it's moving here, friction force toward the center. Now it's moving here, friction force to the center. And it makes the car be able to turn like that. Or I guess, opposite direction because the car is moving in this direction. But if the friction force is insufficient, then it actually can, slide off the road. Okay. All right, so let's talk about then flat or unbanked road, which means basically that the street or the road is flat. That means it doesn't have any incline, any angle with respect to the horizontal. All right, so then in this case, as long as the tires do not slip, the friction is static. If tires to start to slip, the friction is kinetic, which is bad in two ways. Remember, the kinetic friction force is smaller than the static. That means it's even worse. That means you're gonna even more let's say skid off the road. And also the static friction force can point toward the center of the circle, but the kinetic friction force opposes the direction of the motion, making it very difficult to regain control of the car and continue around the curve. So that's why one of the things we want to do here is make sure that, let's say, we are keeping up with some kind of designated speed or something like that given, on the road. So here's an example. So think like this. So car speeds along the curved exit ramp of a freeway. The radius of the curve is 80 meters. A 70-kilogram passenger holds the armrest of the car door with a 220 newtons force in order to keep from sliding across the front seat of the car. Assume the exit ramp is not banked and ignore friction with the car seat. What is the car's speed? All right, so in this case, what we can say here is those are, basically kind of like action reaction forces, right? So the 20 newtons that, passenger exerts on the, armrest, basically the armrest exerts 220 Newton force on the passenger in order to keep passenger be able to, go around, that circular path. So, oops. Here's would be, let's say if I take here's this passenger, the coordinate system like this, then there are two forces that we already can imagine, right? There's a normal force from the seat and there's a gravitational force. But there's also, this, force F, right, applied. So, and this is the one that basically is toward the center, and this is the one that, allows to go around the circle. So, which means that what we can say here is this force, in terms of x direction, F equals mv squared over r. But let's say this is equation 1, equation 2, in the y direction, then we get normal force is equals to mg. Okay. So from here then, since I'm given the force magnitude, mass, and the length, I mean the radius, we can just solve for the, the speed, which will be then square root of Fr over m. Just rearranging that equation 1. Then the speed will be square root of 220 newtons. Okay. 220 newtons times the radius, which is 80 meters. And this is divided by the mass, which is 70 kilograms. So then the speed is going to be 15.9 meter per second. Okay. Which is, if you kind of double this, it will be about 35 miles an hour, which is kind of like the speed that you see generally when there's a, car, turning around on a freeway or something like that. All right. That means every time object kind of, has a flat surface, right, and it's turning, then the friction here is, let's say it's either, sort of force, centripetal force is either friction, or let's say you can think of like, let's say, since when you're turning, right, if you talk about passenger itself, then it's kind of like the normal force, from the car. Let's say, in this case, armrest or something like that. But if you talk about the car itself, let's say, then that force is actually, a static friction pointing toward the center. Equations pretty much will be exactly the same. For the flat surface, normal force equals to mg. If, let's say, the normal force is the only force in a vertical direction against the gravity, and centripetal force is always equals to mv squared over r. Now, here's then another example for the banked road. So you can see, right, a civil engineer wishes to redesign the curved roadway in such a way that a car will not have to rely on friction to round the curve without skidding. In other words, a car moving at the designated speed can negotiate the curve even when the road is covered with ice. Right? So it's actually possible. Such a road is usually banked, which means that the roadway is tilted toward the inside of the curve. Suppose the designated speed of the ramp is to be 13.4 meters per second, which is roughly about 30 miles an hour, and the radius of the curve is 35 meters. At what angle should the curve be banked? All right, so you can see that in the picture over there, right? So this is not a car sliding down or going up, right? It's actually a car driving forward on a banked road. So this is a little bit different compared to how we usually deal with the incline, let's say, problems, because this is not an typical incline problem. So even though the road is banked, but the car is not sliding down or moving upward. So what we generally do in this type of examples, we take our coordinate system, let me make it in the red color. So our coordinate system is actually like this. That means I'm going to be using my typical, X and Y coordinate system, but this time to take toward the center as my positive X direction. Okay. Because in this case, if I have a normal force from the surface, you can see, right, normal force is then perpendicular to the surface, but now in this particular example, happen to be then a two-dimensional force. Again, so let me make it here so you guys can see. So I'm making to the left to be my positive, up. So this is positive Y, this is positive X. Okay, so this is my road. So my road is kind of banked like that. And this is the angle theta. So obviously, if this is my car at the center, right? Again, this car is not sliding down or something like it goes forward, right? So basically, we're looking over the car from above on the road. So the forces that are acting is a normal force, which is perpendicular to the surface. We know that. But the gravity acting straight down, in this case, actually, straight down, happened to be in exactly negative Y direction because I took the coordinate system like that. And the theta of the incline happened to be the theta over here, which means normal force that I have in this case is the two-dimensional force. So it means there's a ny, which is y component, and here's then an x, which is the x component. And then if I'm doing my, force table, then what I have is this. Here's a normal force, here's a weight, okay, and this is net force. So generally what we would do for the incline, have a normal force has no x component, positive y component, but this is not, again, this is not your typical incline, right? Banked road, this is how you approach your, coordinate system. Now, and the normal force has a component. X component is n sine of theta, because you can see, right, it's the opposite to that angle. Y component and cosine theta. So positive, positive, because I take to the left to be positive direction, so that's first quadrant. And weight is straight down, okay? In a y direction, there's nothing there. In the x direction, there's mv squared over r, which means the normal force, or the x component of the normal force right now, acting like a centripetal force. So my equation 1 will be then n sine of theta equals mv squared over r. And equation 2 will be n cosine theta basically equals to mg. All right, so now, remember, what we want to do here is we want to find the theta. But we don't know anything about normal force. What is the normal force value? We're not even given the, the mass of the object. So how do we proceed here? Well, I take equation 1 and divide by equation 2, like we did before. And if I do that, you can see, right, normal force cancel out from equation 1 and 2. Mass cancels out from equation 1 and 2. And I end up with sine over cosine, which is tangent of theta, equals v squared over rg. That's my equation after I divide 1 and 2. Then from here, just solve for theta. Inverse tangent of speed 13.4 squared divided by 35 meters times 9.8. I calculate to get 27.6 degrees. That's my incline angle. That means if this car goes at 13.4 meters per second on a 27.6 degree banked road, doesn't matter if it's full, basically if it's fully covered in ice, this car will be able to make turn. Why? Because the ice or icy surface effect if the car requires friction. But in this particular case, if you banking the road and using the designated speed, there is no friction. All right, so you're basically going such that there is no friction or no friction needed at all. And you can go around on a banked road by having normal force, or the x component of normal force, acting like a centripetal force. See, this is the designated speed. If you go slower than that, then car will start sliding down, so there's going to be friction upward, and then it makes it complicated. If it starts moving faster, then there's a downward friction keeping it on the road, and again, it makes life a little more complicated. But it becomes relatively straightforward if the car can keep the designated speed and move around in a circle like that, right? Like NASCAR, if you look at it, it's really banked, right? And they don't change their tire as often, let's say, as Formula One or other races and things like that. That's because they move such a way that they don't really use too much of friction, okay? And then the surface force, right, the normal force basically able to keep them, going around in a circle like that. All right, so the last type of sort of like, let's say, circular motion that we're going to be considering is what we call loop to loop, okay? And generally there are a couple of things we can look at it from here. So one is sort of like a roller coaster type of thing, right? Or another one is basically like Ferris wheel. And the difference here is that, for example, loop to loop, if you do like a roller coaster, the difference here is that the way you're sitting, right, at the top, you're kind of upside down. Or if you think of like a Ferris wheel, right? Ferris wheel, you basically, same orientation at the top and at the bottom. Okay. So now, just try to be a little bit careful if you're dealing with a, let's say, roller coaster or a Ferris wheel. But here's what we have. In terms of if it's a roller coaster, this is now an example of a non-uniform circular motion, which means the object going around in a circle has different speeds at the top, at the bottom. Okay. And you can see that if I'm looking at the velocity at the top, like that, right? Comparing to the velocity at the bottom, then you can see, right, there are two different, let's say length for those vectors. We know already there is a two different direction because it's going around in a circle. But now we also have different lengths. That means magnitude is not the same. Okay, so it's a non-uniform circular motion. So how do we approach a problem, a problem like this, or set up like that? Well, we have to understand that there is still a net centripetal force if the object going around in a circle that is toward the center. And we need to understand that there are right now multiple forces acting in a radial direction. So let's first look at the bottom. Okay, so here's what happens at the bottom. When the roller coaster, right, it's kind of like this, right? When it's at the bottom, think like this. See how the person sitting, right? So there's a normal force upward and then the gravity downward. But technically the person is going around in a circle, means that toward the center, the force that is toward the center is stronger than the force opposite, of the center, which means normal force is greater. And if I take center to be my positive direction, my net force, radial net force, right, is basically normal force minus mg, because normal force is positive, mg is negative, so I have their difference, which is m times radial acceleration. Well, radial or centripetal acceleration is then speed squared divided by radius. But this is speed at the bottom. And you can see if you rearrange, becomes normal force equals mg. Since this is negative, you move it to the other side, becomes positive, so it's mg plus mv squared over r, which means that normal force is greater than, a gravitational force, right? Let me put it like this, is greater than mg, greater than gravitational force. Okay, and it has to be, right? Because in order for there to be upward net force, the normal force has to be greater than gravitational force. All right, so then how about at the bottom? Sorry, at the top. That was at the bottom. Now how about at the top? Well, at the top, if you kind of go back and see what the way the roller coaster, right? The car is oriented. See, the person is upside down. That means normal force is down, but so is gravity. That means both of them are, in the same direction. That means when we're doing the net force in a radial direction, it's normal force plus gravity. And again, taking down as positive direction, both of them down, so both of them are positive. Now their sum is equals to mv squared over r. So what do we do if I'm solving for the normal force? If I move the mg to the other side, then it becomes negative. Then I can see that normal force is equals to mv squared over r minus mg. Okay, that means what I have here is generally normal force then is less than gravitational force. Okay, it doesn't have to be as strong because now it has helps. Gravity and normal force together give you the net force. Okay, which then if you calculate f top or let's say f bottom, you will be able to see, let's say, in terms of their differences, right? But now here's what we get. If I'm looking at the top, and this is very important, let's say if you're designing roller coaster or something like that. So this is the equation you're working with at the top, where this is a term where it's mass times speed squared over radius minus mg. Okay, that's what your normal force is. Normal force means that when the roller coaster going around and you're at the top, remember, if normal force is non-zero, right, you're on your seat and you're able to, basically this is going around, you're safely on your seat. But here's the thing, mg is a constant, right? Your mass times 9.8 doesn't change. But this first term, mass times speed squared over r doesn't change, for example, right? Because it's the rails, right? But speed can change, right? If you're moving faster and faster and faster, or slower and slower and slower. And the idea here is this. At the top, the normal force on the truck, on the car here, is given with this equation, which is the same equation as in the previous slide. But if this roller coaster, right, if the cart or the truck start basically going slower and slower and slower, that means this V top, right, this V right at the top starts decreasing, okay? And if it starts decreasing, then it's possible that this term eventually gonna, decrease until it equals to mg. So let's say if this is equals to mg, then it becomes mg minus mg, you get 0, which means normal force is 0. That means as you slowing down, at some point the speed is such that this term is equivalent to mg, and the normal force equals 0. So this is known as a critical speed, because then if you're saying mv squared over r minus mg equals 0, that means mv squared over r is equals to mg. You cancel the mass, then you can see, right, v is nothing but, square root of rg, which means that you can calculate your critical speed. I don't know, let's say 20 meters per second. Because anything above this, you're safe. At this speed, you're still kind of safe, because even though the normal force is 0, you still have enough speed that can, the roller coaster can still take you down safely. So, but what happens when, your speed is slower than, let's say, this critical speed? Well, that's kind of what this diagram shows. See, any speed greater than critical speed, no problem. You are going around in a circle. At critical speed, there is no normal force. You kind of off your seat a little bit as you're going around, but still it has enough speed that kind of keeps you on the rail and you go down. But that means you basically reach the critical height. But when your critical speed is less, or your speed is less than critical speed, then your, let's say, maximum height becomes less than critical height, right? So let's say, and then the car or the track, right? So basically goes off the rails. So this is basically what you end up with, some parabolic trajectory. That means the speed is not high enough and you reach the highest point earlier than you should. So then after that, you're kind of going down, but you're already, unfortunately, no longer on the rails. So that's why it's important to sort of, like, let's say, keep, speed at least at critical speed. So let's look at an example like this. A 500-gram ball moves in a vertical circle on a 102 centimeter long string. If the speed at top is 4 meters per second, then the speed at the bottom will be 7.5 meters per second. It's a non-uniform, circular motion. Okay. What is the gravitational force acting on the ball? And what is the tension in the string when the ball is at the top? What is the tension of the string when the ball is at the bottom? So think like this. So here's, you have a ball, and here's a string, right? And you kind of make it kind of like go around in a circle like this. Okay. So what is let's say, the gravitational force or the weight? Well, it's simple. Part A is simple. It's just mg. And you have a 0.5 kilogram ball times 9.8, right? Basically like, half of 9.8. So you get 4.9 newtons. That's the gravitational force. And it's always going to be constant. All right, so now let me kind of like do this sort of like, let's say, part of it, so it's a little bit cleaner like this. So when it's at the bottom, the forces acting on it is gravity and then the tension. Now the question is that which one should be stronger? Well, remember, it has a net force, centripetal force at the top toward the center. That means the tension should be higher. So tension minus weight should then equals to mv squared over r. Okay, this is your net radial forces. Okay. So then the tension is equals to mv squared over r plus mg, which is the weight. That means we can solve for B, right? We can then solve for the tension. Okay. Then I can say, all right, so I can factor out mass, which is 0.5 kilograms. The rest I can basically leave it there. Since this is at the bottom, is 7.5 meter per second squared divided by a radius of 1.02 meters, then plus the the weight, which we just calculated as 4.9 newtons. All right, so I calculate this. Oh, never mind. I factor out the mass, right? So this is just 9.8 meter per second squared. All right, so we calculate this. I'm going to get 2. No, right? This is 32 newtons. That's the tension, 32 newtons. And you can see, right, it's much higher than the gravitational force. It has to be much higher than gravitational force in order to do that. And then you have at the top. So at the top, this is your weight. And then, This is still the string, so this is also the tension. That means tension plus mg, right? So both of them in the same direction equals mv squared, and this is, I should put like at the bottom, this is at the top, or mv squared over r. And then tension will be mv squared over r minus mg in this case. Again, if I do the same calculation, that means take, put the mass, speed at the speed at the top, which is 4.4 meter per second square, right? 4.0 meter per second square. And you just do the same calculation, right? What we'll see here is then 2.9 newtons. And as I mentioned, right at the top, then it should be less than gravity because it, it doesn't need to be, strong. Both of them are in the same direction. Because remember, going down, it's actually speeding up. But going up, it has to slow down. So the tension has to be really strong enough so when gravity is all the time acting against it and slowing it down, it has enough speed to go all the way to the top. Okay, so that's kind of what we have with this. All right, so the last type of force we're going to consider, well, maybe not, we have one more. So another type of force we're going to consider, which is kind of like resistive, is what we call air resistance, basically. So when moving object moves through a medium, the medium exerts a resistive force R on the object. This could be in water, this could be in air, right? So mostly like, let's say in some kind of medium like air, for example. So the magnitude of R depends on the medium. Direction of R is always opposite the direction of the motion of the object relative to the medium. So that's why it's kind of like a resistive, like a friction. It's a resistive force always against the direction. Nearly always increases with increasing speed. All right, so we have some kind of, a model that we can use. For example, R is some kind of resistive force, and it equals to negative B times V. Negative because it's acting against the direction of the motion. So B is some kind of constant, which we're gonna, assume some kind of proportionality constant depending on the properties of medium and so on and so forth. V is the, is the velocity of the object. So that's why you can see, right? It's acting in the opposite direction of the velocity always. And it's proportional to the velocity. So sometimes you can also look at when the R here is proportional to the velocity squared or the speed squared. So this is generally what we use for the air resistance, right? So whenever object going through the air, the resistive force is approximately proportional to the square of the speed. That means in a way, everything else is basically your B, right? So and you can see, right, this is also known sometimes as drag force, right? So that's why this D here is known as a drag coefficient. So it is known as a drag force. And this is basically another name for the air resistance. So 1/2 times D, which is this is kind of like a coefficient, just like coefficient of friction, right? Then density of air, rho is the density of air, A is the cross-sectional area of the object, then V is the speed. So that's why, for example, if you have a paper like this and then some compact object like that, this object can have no problem going through air and have a very little air resistance, where the paper has all that surface area that interacts with air molecules. So then paper has, a lot higher air resistance effect than some kind of, small piece of paper or like small rock or something like that. So that's kind of what we have. And this affects object that kind of going through the motion in air, right? Or like, let's say in liquid or thing like that. So for example, let's say you're dropping an object from a really up high, let's say from a helicopter or something like that. What happens here is the object, from going down from the helicopter is initially going down because gravity's pull. But as its, speed increases and it's going through the air molecules, right? Then there's a lot of, resistance from air molecules. And then what you have here is that, let's say this is it initially when it was just a gravitational force mg, right? Straight down. Now there is also a resistive force in the opposite direction. Remember, it increases with speed. That means as it's going down, speed is increasing, so this R is increasing. And at some point, as long as mg is greater than R, the object is speeding up as it's going down. But as soon as, speed increases, let's say significantly enough that R, remember R is dependent on speed, right? So let's say you have this mg minus 1/2 d rho av square, which is basically nothing but, weight minus this R, right, equals mass times acceleration. As long as weight is greater than R, you are speeding up down. But then at some point, speed is strong enough that this term is equal to that term. What happens then? Then this is equals to 0. Okay, this is equals to 0, which you can see right sort of like in this equation. This is the acceleration, which is g minus d rho a over 2m, right? But at some point, you know, what we have is, you know, let's say you can get a speed where, let's say the object has equal amount of gravitational and resistive force. So in that case, what we can see is that then mg is equals to 1/2 d rho a v squared. So from here, we can say then you can calculate the speed, which is square root of then 2 mg divided by d rho times a. So this is known as a terminal speed, terminal velocity. So terminal velocity, which means now object, once it reaches this speed, it's no longer going to speed up. So it's going to just basically maintain that speed. So that's the interesting thing, because object then falling right from the helicopter only going to speed up for a little bit until resistive force is equal to the gravitational force. Then after that, it's basically going at the same speed, constant speed. It's not speeding up. It will be bad if objects like anything small, that even if it's going down, it's speeding up the entire time. When it hits the ground, it's going to be hitting the ground with insane amount of speed. But luckily that doesn't happen, because the air resistance slows it down and eventually makes it go at some constant speed. And it doesn't speed up all the way to the ground. All right. The very last example that we're going to see here of a force here is one of the fundamental forces. This is force of gravity. This is generally when you have any two objects with mass, let's say m1 and m2, they exert gravitational force on one another. Now, we know about weight as a gravitational force, but there's also more universal gravitational force, like let's say, not in terms of like how the Earth affects some object, right? But let's say how Earth and Moon affect each other, how Earth and Sun affect each other, how two planets, two stars affect each other, how two galaxies affect each other. That means any object that has mass exerts gravitational force on another object that also has mass. And this gravitational force is proportional to the product of the mass of object 1 and object 2, then inversely proportional to the distance squared from center to center of 1 and 2. Now, going from proportionality sign to equal sign, then we introduce a constant, and that's this gravitational, universal gravitational constant, G. All right, so we'll look at this equation a little bit later on in this semester. But the idea here is that there's also this equation that gives you more general gravitational force, mutual gravitational force with any two objects, which is action-reaction force. That means any two objects with mass exert attractive force on one another. Action-reaction force, that means one will be attracted, two exert force on one exerts force on two, and those forces are attractive. The reason right now that, for example, you're not attracted to any other object of mass m around you, because that force is extremely small if the masses are small. And only, you can feel its effect if you're considering at least one of the object is, a really large, like, a moon or a star or a planet or something like that. Otherwise, this effect is basically extremely tiny. All right, that's it for this chapter.